In today's video, we're looking at some simple geometry to do with the Argand plane, which is going to make your life easier. Because it turns out mathematicians weren't terribly happy with complex numbers for quite a while. We've made up this number I and just run with it and see that things just kind of work nicely, but it's not very rigorous. It's a bit, what's the word? It's a bit dodgy, I guess. But once mathematicians realized that we can think of these complex numbers as points on a plane, then all of a sudden the arithmetic's just geometric. Finding multiplications is just a geometry problem. Finding powers and solutions to certain simple polynomials, turns out it's got a geometric interpretation. And all of a sudden, complex numbers aren't so strange anymore. They're just this geometrical object. And we've been working with geometry for thousands upon thousands of years. So that's kind of the impetus that led to us accepting these complex numbers a little bit more. I mean, nowadays we have a much more rigorous and mathematical definition of what these complex numbers are in terms of number systems. But the geometry idea kind of helped bring them to acceptance. So the first thing we're going to look at is the idea of the conjugate. I think I've already showed this, I can't remember now to be honest, but geometrically if I've got a complex number z, let's say z equals a plus ib, if I plot it on the Argand plane like this, then its conjugate, z equals a minus ib, is at the same distance along the x-axis, the real axis, but then I travel down the y-axis, the imaginary axis, instead of up. And you can see it's just a reflection of the complex number z in the x-axis, the real axis. Now the point z, or the complex numbers z and negative z, have the same kind of idea to them, except this time it's not a reflection in just the x-axis, it's also a reflection in the y-axis as well, because both components, the real part and the imaginary part, have been negated, and therefore you can also think of it as a rotation of 180 degrees. It's been rotated pi units if we're working in radians. Now multiplying by I is a special case. Let's suppose we have z1 equals a plus ib, and z2 equals I z1. Then let's multiply through. So we get IA plus I squared b, or since I squared is -1, negative b plus IA. And let's plot them on the Argand plane, and then let's consider the line segments OZ1 and OZ2. If we look at the product of their gradients, then we see it's going to be BA times A on negative B, which when I multiply through just gives me -1. In other words, they're perpendicular to one another. And if we look at the diagram, it's easy to see that Z2 is in fact a rotation of pi on 2 radians counterclockwise. So in general, multiplying by I means that I rotate my original complex number, the point representing that complex number, pi on 2 radians counterclockwise. So just like in a Cartesian plane, I can plot curves on the Argand plane, and then we can have a think about, well, what does that mean in terms of complex numbers? So for instance here I can see I've got the vertical line going through x equals 2. Well, that's representing any complex number that has real part 2. In other words, REZ equals 2. And then I've drawn this horizontal line, IMZ equals -1, because it's going through the point on the y-axis -1. It's representing any complex number that has imaginary part -1. And in fact, if we think again geometrically, where do those two lines intersect? They intersect at the point 2, -1, which is representing the complex number 2 minus I. Okay, again, let's think geometrically in terms of complex numbers. Let's suppose I have a complex number x plus iy, and I know that zz bar equals 9. So the complex number multiplied by its conjugate gives me 9. Let's have a look at what that looks like on the Argand plane if I plot that result. So any complex number, but its product with its conjugate has to equal 9. What happens? Well, let's actually do the maths. Let's actually expand x plus iy times x minus iy, and we know that's got to equal 9. Then when I do that, I get x squared plus y squared equals 9. That's a circle centered on the origin with radius 3. Here's a harder example. Let's suppose we have 1 on z plus 1 on z bar, and we know that that's equal to 1. Let's see what happens. Well, I've got two fractions. They don't have the same denominator, so let's fix that up first. So I'm going to have to multiply by the lowest common multiple, and I'm going to end up with z bar plus z on z bar is equal to 1. Multiply across to get rid of the denominator, and I get z plus z bar is equal to z bar. Well, if z's x plus iy, then z plus z bar is x plus iy plus x minus iy. The imaginary parts cancel, and I just get 2x on the left-hand side. And similarly, z times z bar, I already know from the previous example, and this always happens when I multiply z by z bar, I just get x squared plus y squared. And when I bring everything over to one side, I get x squared minus 2xy plus y squared is equal to 0. And I can complete the square there, and I get x minus 1 all squared plus y squared is equal to 1. And that's a circle centered at 1, 0 with a radius of 1. But what we do have to remember here, and this is what makes this a harder example, if I just drew that circle in, so centered at 1, 0 with a radius of 1, I'd be including the origin, 0, 0. But that can't happen because the original problem was 1 on z plus 1 on z bar equals 1. I can't have z equals 0. Otherwise I've got an undefined fraction there. So in fact, this is that circle, but I need to acknowledge that the origin actually has an open dot. That's what made this a harder example. So sometimes we do have to actually think very carefully, are there any restrictions to this problem that I need to include in my solution? And that's it.